quantum computing, the qubit. You hear these words thrown around all the time. And honestly, they sound like they're straight out of science fiction. But what is a qubit really? Like, what is it physically? Today, we're going to pull back the curtain and look at the actual engineering blueprint for building the very heart of a quantum computer.
Okay, let's just dive right in. If you think of a quantum computer as this revolutionary new engine that's going to change everything, then the qubit is its absolute core, its beating heart. So the most fundamental question is, how do you actually build one? What are we even talking about making here? All right, first things first, let's get a really important comparison out of the way. On the left, that's the classical bit. It powers every piece of tech you own. It's simple, right? It's a switch, either off or on, a 0 or a 1. But a qubit, well, a qubit plays by the bizarre rules of quantum mechanics. It can be a 0, it can be a 1, and thanks to this wild property called superposition, it can be both at the same time. Just imagine a spinning coin. Before it lands, it's not really heads or tails, is it? It's kind of both. That's the secret sauce of a qubit. So let's leave that simple on or off switch behind and get into the nitty-gritty, the physical reality of what it takes to make one of these incredibly powerful quantum objects. And this right here gets to the absolute heart of it. See, a qubit isn't just some abstract concept. It's a real physical thing. A tiny, ridiculously isolated quantum system. We are literally talking about capturing and controlling a single electron, a single atom, or even a single particle of light, a photon, and then using its natural quantum weirdness to represent information. So how in the world do scientists actually do that? It sounds kind of impossible, but it turns out that even though there are different ways to make a qubit, they all pretty much follow the same general recipe. And here's that recipe broken down into 4 key steps. First up, you have to identify your quantum system. You got to pick which particle you're going to try and wrangle. Second, you have to isolate and control it. This means trapping it somehow and then using amazing tools like lasers or microwaves to poke it and manipulate its state. Third, you fabricate the teeny tiny structures you need to hold and control it, which often borrows tech from the semiconductor industry. And finally, for most of them, you have to cool it down, way down, to keep it stable. So let's take a walk through how this blueprint is being used in the real world. Because it turns out there isn't just one type of qubit. It's more like a whole gallery of different designs, all in a race with each other, and each one has its own unique strengths and weaknesses. Our first stop in the gallery is one of the most popular designs out there, the superconducting qubit. At its core, it's a tiny electrical circuit, but it's made from special materials that have literally 0 electrical resistance when they get super cold. But the most exciting part? It's all built on a silicon chip, which should sound very familiar. So how are they made? Well, the really crucial part is that they're built using lithography, a process that's very similar to how we make the chips in our computers and phones. That is a huge advantage, because it means we can potentially scale them up using technology we already have. And for control, scientists just send these super precise microwave pulses into the circuit to gently nudge it into the 0, the 1, or that all-powerful both state. Next in our gallery is a completely different philosophy, the trapped ion qubit. Okay, forget circuits. For this one, scientists take a single atom, they give it an electric charge so it becomes an ion, and then they trap it in midair, inside a vacuum, using electromagnetic fields. I mean, think about that. We are literally holding a single atom perfectly still in space. It's wild. So how on earth do you control a single floating atom? The answer? Lasers. Incredibly precise laser beams are aimed at that one little ion to change its internal energy levels. A low energy level can be your 0, and a higher energy level becomes your 1. The big strength here is that these are incredibly stable and can hold their quantum information for a very long time. It is an absolutely mind-boggling feat of precision engineering. So you've got superconducting circuits and trapped ions as 2 of the big frontrunners. But trust me, the race to build the perfect qubit is far from over. There are other brilliant teams betting on completely different and equally fascinating ideas. Let's just quickly peek at 2 other contenders. You've got quantum dots, which people call artificial atoms. These are tiny semiconductor structures designed to trap just one single electron, and they use its natural spin, you can think of it like a tiny magnet pointing up or down, as the qubit. And then there are photonic qubits, which use individual particles of light, photons, and encode information in things like their polarization. So we have all of these incredible, delicate, genius designs. But nearly all of them run smack into one enormous and, well, Very, very cold, hard truth. Here's the thing. Quantum states are just unbelievably fragile. The slightest vibration, the tiniest whisper of heat from the outside world, what scientists call thermal noise, can instantly destroy all that precious quantum information. To make a qubit work, you have to create an environment for it that is almost perfectly silent and perfectly still. And when we say you have to protect it, what we really mean is you have to get it cold, unimaginably cold. Just look at this number. We are talking about temperatures near absolute zero, just fractions of a degree above the point where all atomic motion is supposed to stop. That is literally colder than the empty vacuum of deep space. It's one of the single biggest engineering hurdles in all of quantum computing. So, what's the big takeaway from all of this? It doesn't matter what the design is, a circuit, a trapped atom, a particle of light. Building a qubit is ultimately a game of extreme isolation and precision control. It's all about grabbing a tiny, fragile piece of the quantum world and shielding it completely from our noisy, chaotic, classical world. And so, that's the state of the art, which leaves us with one final and really thrilling question. We've seen circuits on chips and atoms held by lasers, each with incredible potential. All these different blueprints are in a dead heat to build the first truly powerful, scalable quantum computers. The only question left is, which of these amazing architectures will be the one to win the race?